So, John, you know what? You can't spell procrastinate without prostate.
Yeah, that's true.
That's true. Unfortunately, a lot of people make their prostate gland the procrastinate gland and don't do it. Get it checked. It's October.
Hey, y'all, it's Dr. Know-It-All. Guess who I am with again? It's Dr. Scott Walter. This is slightly last minute because October 3rd, which is yesterday as we're recording this, Google DeepMind put out a really interesting paper and a repository and a blog. We're going to mostly cover the blog, but I actually wanted to start with, let's see if we can find it here. I wanted to start with the paper simply because this just cracked me up. I was like, I could not believe how many authors are actually listed here. It's a pretty impressive number of authors on this thing. It's a 6-page paper with, I don't know, 100 authors, something like that. But anyway, yeah, Scott, welcome. And we are going to spend most of the time taking a look at this thing. And of course, we will put a link to this in the description so you can check it out yourself and go from there. Yeah. So you're in Michigan right now, Scott, right?
Yeah, I am. And when you mentioned October 3rd, it just reminded me that yesterday was Deutsche Einheitstag.
Okay.
Which means like the German unification day. This is the day they celebrate the unification of the two. Oh, that was yesterday, the 3rd.
Right.
Here we are on the 4th. So
it's John, October 4th.
Aren't you obliged to read all the authorships? Aren't you obliged to read all the names on the authorship?
I'm going to put this on here so somebody can freeze frame it if they want to. Also, I do want to point out that in I don't know, appreciation of this, I'm wearing my Robot Love t-shirt. I know that that's a Tesla thing, but this is one of those rising tide lifts all boats kind of deals. This is not competition. This is, I mean, it is competition, but it's actually the best kind of competition. The first thing I discovered about this was we were wrong about RT1 being the name of the robot. That is actually apparently the name of the architecture that they're using. And now, and they have RT1, RT2, and now this is RTX, which is an improvement over these last. So I assume that just means robot training. It was robot training 1, robot training 2, and robot training X. So again, DeepMind purchased by Google. They are a bunch of very, very smart people, including, of course, the founder, Denis Hassabis. So yeah, where do you want to start with this? You want to start with the little videos of things or kind of the big picture overview? This is useless, by the way. I don't know why they even threw this YouTube animation in. I played it and I was like, that's stupid. Yeah, let's go down here to here. And let me see if I can blow this up a little bit and make these.
I think part of it is Jim Fan. Yesterday, he mentioned something about that this is like an ImageNet moment.
Yes.
And maybe you want to give a little bit of the background on ImageNet and what he's really talking about and why he's using that as a parallel.
Okay. So I think I'll just leave this up here. So ImageNet 2012, previous to 2012, in the early 2000s, a consortium that called themselves ImageNet put together a really, at the time, unprecedentedly large, approximately 1 million images sized database. And this was a huge, changeover. I think the big one before that was MNIST, which is National Institute of something or other. And it was those little tiny numbers that are like 32 by 32. Anyway, so this was a huge jump forward in the state of the art. And every year they had a competition to see who could figure out whether, or who could get the best image classification out of their network. And people were getting above random chance, which was good, but these were a lot of very complicated coded things using support vector machines and principal component analysis and a bunch of other very heavily heuristic code. Along comes Alex, and I'm forgetting his last name. I feel really bad. And Jeff Hinton.
But it was called, I think it was called AlexNet, I think was the name of.
Yes. It's AlexNet after Alex, who was one of the people. And I always forget his last name. I'm terrible about that. But anyway, so Jeff Hinton and he at University of Toronto put this thing together using deep neural networks, the first kind of major deep neural network that was attempted. And they jumped from like getting 20% correct on these classifications, and it's 1,000 categories. So even 20% is pretty reasonable, to getting, if I'm remembering correctly, it was about 2/3, around 67%. So it was like this step change. And that's considered to be the ImageNet moment. This is late 2012 when this happened. So we're about a decade later, 11 years. And so the idea is that this now is sort of the ImageNet moment for robotics. So I don't know, Scott, why don't you take that away?
Is it the ImageNet moment or not? Because my understanding is that ImageNet was this idea, we've got to start collecting all these things and start having these
Yes.
competitions. And we were
Right.
slowly getting better. And suddenly AlexNet came out and just, like you said, the step change. And everyone was like, whoa. And I think, isn't that when like neural nets more or less came out of the wilderness? Because everyone
Yes.
had been saying there was so much promise to neural nets. And
Right.
they're like, forget it. You can't do anything with it. And suddenly they proved that you
Right.
actually can do it with the neural nets. And that's when everyone took a second and third and fourth look at neural nets and decided, and that
Right.
began that revolution. Right now, I think what this is, it's more or less announcing that we are setting up something like ImageNet, which is now a repository of all these videos
Right.
from all these robots around the world, all sorts of research. And now that we have that database in place, you can start to come in and do your research and training on that. So
Right.
we've got the ImageNet moment, but we don't have what I think was really the AlexNet moment. That was
Yes.
when suddenly you got that step change. So now we've got the network that everyone can go into, or the huge database for training
Right.
data. We're probably going to start seeing competitions, yearly competitions.
Right.
And then who knows whether it's going to be like 5 years, which I think it was for ImageNet, before suddenly it's like, whoa, this big
Yeah.
step change kind of happens.
I,
And then everything's
I think I combine this into both a little bit, because
yeah.
if we scroll down to the emergent behavior,
Yeah.
here,
So it's,
this graph right here is very impressive.
Mhm.
There's basically a 3x improvement in emergent behavior, which is basically that you take the robot, and the thing that's it's really important to know is that this robot is kind of abstracted robot. It's an arm, but it could be any of, I think, 30, if I'm remembering correctly, different robots, actual physical robots that are doing this. But that it's able to do a task that it has never been asked to do before. So I think, yes, number one, it's fantastic to see this massive cross-disciplinary data set of all of these robotics things. But I think it also is a little bit of the AlexNet moment as well. And maybe we'll see another one that comes later, but this is a very impressive figure right here.
Yes.
I know most people might be like, whatever, but it's like that blew my mind when I saw that. And I was like, okay, we got to do a video on that. So yeah, I think it's a little bit of both, although we might see something significantly better in the future. But yeah, 33 academic labs. So 22 different robot types to create the OpenX embodiment data set,
Right.
And
right.
the RTX model. So they're, I believe, giving away the RTX model. Let's see if I'm correct about that. Yeah, release R1X, a robot transformer, not robot training, sorry, derived from the RT1 and trained our data set. So this is super cool that they're releasing most of this stuff.
The training set, which is videos. And the question is, are there enough videos out there? Because everyone agrees you need a lot of videos to really be able to get it to go.
Right.
So now we're talking about maybe an adequate training set to do a lot of that. I'm not surprised that it's good that they show they can do it across different robot types. So you should be able to abstract that out. I think somewhere in there, they talk about what the output vector is. And it's basically a Cartesian coordinate, which means it's independent of any kind of robot manipulator. And then it's going to be up to you to sort of take that output and maybe through heuristics, which typically is how it would be done, or it can be done maybe through a neural network, then say, okay, now train what the arm has to do to get to that location. So it's not actually joint values you're getting out, because if you're getting joint values out, then suddenly you're heavily robot dependent.
Exactly.
And now it's not. So it's been abstracted enough and is more or less just showing the tasks, and it has to figure out what would I do to get there. And then once you have those XYZ locations and the orientations, then your control system will figure out what do I do to actually go there. And so I think they said in there, I might be confusing it with another paper, that there's 7 outputs, because the RT2 paper talked about 7 outputs: XYZ, yaw, pitch, roll, and gripper status, closed or open. And the only thing I hesitate, I don't know if they plan on changing it, is I don't like using yaw, pitch, roll to describe an orientation, or for that matter, 3 angles of anything, because there are positions in there which are quasi-singular that you have to be aware of. So it's really hard to take any orientation space, and sometimes there'll be some yaw, pitch, roll coordinates which will be a bit vague. And so I would prefer that they use something like quaternions to be able to determine that. But that maybe they'll do that eventually, and then it should actually be 8 properties. So you need 4 properties really to nail the orientation in a way that you're not going to have these weird mathematical side effects that will happen later on.
Right. Yeah. And those are, they're not really nitpicky, honestly, because they actually, they do seem like they would make a big difference. But the important part is to most people, the general populace, is you're abstracting this from individual robots. It's not the amount of voltage that you've applied to a particular actuator or something, which is ultimately what it has to be translated into to make the thing move. It's more abstracted than that. And that last little bit is something that you can do individually with your robot to translate those things.
That's trivial. That's really trivial compared to everything else. Absolutely.
Right. And so this data set is huge. So here, I just wanted to read this. So yeah, this is like the ImageNet propelled computer vision research. We believe OpenX embodiment can do the same to advanced robotics. Building a data set of diverse robot demonstrations is the key step to training a generalist model. And this is what we're going to talk about a lot. I think you said cross-training is the way to like get a better athlete. So it's like cross-training.
It is definitely cross-training. Yep, exactly. CrossFit.
Yeah, CrossFit. There we go. Yeah.
So anyway, we call it cross training, but yeah, it's like, yeah, well, yeah, since we're fitting data, maybe that's what we call it, CrossFit.
CrossFit. That's actually really good. See, you named
with an X. You can use an X already. X-fit. There you go.
XFit. So if OpenAI is looking at this, they can do XFit. So
yeah.
Anyway, so they can control many different types of robots, which again is that abstraction from the particular robot, follow diverse instructions, perform basic reasoning about complex tasks, and generalize effectively. That's also important. Too resource intensive for any single lab. To develop the OpenX embodiment data set, we partnered with academic research labs across more than 20 institutions to gather data from 22 robot embodiments demonstrating more than 500 skills and 150,000 tasks with more than 1 million episodes, which would be the video sequences. Now, I assume that's video sequences plus the data about Cartesian coordinates and stuff. I'm not exactly sure.
Yes. Yes. Yeah. Oh, guess what? It's 220.
Right.
It's 220, John. What's happening at 220 across the entire US right now?
I have no idea what's happening across.
Everyone's phone's going to blow up. Everyone's phone right now. So basically, my phone's blowing up because it's a national test of the nationwide alert system.
Oh, I've got do not disturb on. So there we go.
Oh, lucky you. So there we go. So everyone can tell it's like 2:20 in the afternoon. My phone, well, 2:18. They were a couple minutes early.
Right. I don't think I got anything.
Hear it again. You know why? Yep.
Well, you know exactly what time we're recording this. So there you go. So anyway, I mean, a million episodes. So we've the ImageNet was approximately 1 million images. This is approximately 1 million episodes of robotic stuff, which would be video plus Cartesian coordinate information about this. So that's the kind of big picture takeaway. The important part here is we get a generalist model. Oh, there it is. I got mine late.
I knew it.
Oh my goodness. Sorry, people. Oh goodness. I would have been terrified if I hadn't known ahead of time that you told me it was going to be alerted for that.
Asteroid impact, 2 minutes. Yeah.
I have been working very hard this week on something that I'm not going to talk to people about because I don't want to jinx it. But if it happens, it's for my company, not for YouTube or anything. But anyway, if it happens, I'll let everybody know because it's really big news if it does work out. So anyway, but yeah, so I've been having my head buried and not really paying attention. So anyway, yep. Okay. Everybody will know when you see this video, that was the moment when your phone went off across the nation, at least in the United States. You'll be like, oh yeah, that's when they were recording this. So anyway, we get training a generalist model, which is really, really the important part of this, is that no longer is it, if you train one model on one robot, that's all it's useful for. It doesn't work on anything else. And that's where we get this other stuff. So we get data sets here, the Franca data set, XARM data set, Sawyer, Google Robot. So these are, I guess this is number of data sets, not episodes. So it looks like there's like 24 of the Franca ones, and then all the way down to one data set each for all of these other guys. But combining them together,
you get Sawyer and Baxter in there. Okay. Yep.
Yeah. But I mean, like Sawyer's got like 4 data sets, and then it looks like XARM has 6. So these are, I don't know the number of individual events in each data set, but that's what they've got in these data sets. And then moving on to common skills, you can see picking is a big one. So what is that? Over 600,000 like videos, I guess, individual episodes, as they call it, for that, all the way down to just a few thousand for things like keeping, turning on, assembling, wiping. So these guys are like the things that it does with the least amount of episodes recorded all the way up to picking and moving, which are very, very big. So everybody loves picking.
Well, if you look at
that's
it,
the one.
it looks like Bedford's law.
Yeah.
You know, there's certain things that you tend to do a lot of and others not so much.
Right.
So
Right.
yeah, you have to look at it that way.
Yeah. I don't know about the navigating because I don't know exactly what I thought the robot was just the arm. So I don't.
Well, the navigating could be trying to pick up something and move it over to here without hitting something else that might be in the way. So it's like
Right.
collision
Right.
avoidance.
Yeah.
It's not necessarily like a mobile robot trying to navigate the streets or anything like that.
Right.
They might be referring to it that way. How to get there without knocking something over.
So yeah. So anyway, so you can see that there are a number of different tasks. And then, it builds on two of our robot transformer models, our RT1 and RT2, and also our vision action language, which we talked about in a previous video. And I'll put a link to that probably at the end of this video as well. But anyway, I'll put a link to that so you can see the Googlebot episode that we already did. But this ties directly back into what we think is going on with Optimus, which is the integration of a large language model into the model of the Optimus robot as well, which is again why this particular shirt. But but basically what they've done is they've broken down the movement of the robot into a text-based movement system, which not only allows it to abstract it, because of course that's if they're using Cartesian coordinates, that's something that any robot could read, but it also allows it to remember tasks because you can essentially like a dictionary. You can say the task of putting is in this, this dictionary. And then there's like entries that you could look at with that. So you can tie a sort of a requested action to a particular set of moves and utilize that as your sort of starting place. At least that's what I understand. Hopefully that's more or less correct. Yeah. So there we got diverse cross embodiment data they're trained on. And they improve models trained on specific domains and exhibit better generalization and new capabilities. So the competition here, when we go down to this, is competing on robots that are specifically trained to do these tasks versus the dark blue line, which is the RT1-X. Which is a generalist model. It's not trained on anything in particular, similar to the way that ChatGPT works, which is that it's a generalist model. It's not only trained on legal documents or something, or medical documents or whatever that is. So the shocking part of ChatGPT when it came out was that it performed so well on specialist tasks when it only was, in fact, very often it performs better on specialist tasks than a language model that was only trained on those specialist tasks. So there is just like with a human being, like we were saying at the beginning, cross-training, that gives you an advantage as an athlete over, and certainly up here as well, mentally, you don't only take one subject in class. If you grew up only taking math class, you're not going to be as good a mathematician as you would be if you took other diverse classes because you need the input from different sources. So yeah, that's basically it.
Yeah. So you basically want diverse disciplines as well. Makes everyone better. So
yeah,
pretty much it means that the ChatGPT is maybe it's not so much a generalist, but more or less like a Renaissance person.
Yes. There you
go. Because it draws from so many different disciplines that it's able to then get the creativity that you'd be lacking if you were just have that very, very narrow focus.
Right.
So yeah, no doubt about it. It's at first it seemed like that can't be right. I mean, that's weird. The specialist should be better, especially for the machine learning. You sort of understand that people, sometimes to become better at something, it's best to do something else because then you will activate something else to do it. And so maybe it does make sense when you start thinking about it more, but at first it was like, that can't be right. The specialist is always gonna be better. When it comes to brain surgery, I want to see the specialist brain surgeon. I'm not going to go to my GP and say, I'm going to have brain surgery.
But I think a human analogy
looks like maybe you do.
Yeah. No. I think the human analogy is appropriate though. The specialist brain surgeon went to primary school, went to high school, went to college, then went to medical school and started really focusing. For all of those years, he or she has been gathering generalist data, and so the idea would be that something like ChatGPT, if you wanted a medical version of that, you take the basic model and fine tune it. You don't start from scratch Oh,
Yep.
yeah, exactly.
You don't
So
train
that's
it
what
pure
looks like
on
happening
medical
here.
stuff.
Right.
Mhm.
The one thing that it lost at, interestingly enough, is Auto Lab at UC Berkeley, which looks like it's a ResNet plus MLP. So I don't know. I guess the ResNet must be the teal line here, which only did like 24%. And then, but if you combine that with a multi-layer perceptron, it gets up to 53. Mean success rate. So there still is room for improvement here, because the best of any of these is only 80% success rate. So, it's a long way from 100, and some of these like 45 and 50, that's only half the time it's getting it right. But you can also see that overall average of doing tasks is 63% for the RT-1-X. So anyway, it's very interesting to see that, and also that it wasn't the best at anything. But these other ones are specialist things that are trained specifically on these tasks. So that's the interesting thing about that. Yeah. So anyway, let's see. So then we get down to some videos that we can watch. So we have it's like, this is a picking and placing, I guess. It looks like it's picking up this thing. And these are the original, like these guys are, this is the silver at NYU. This is rail at UC Berkeley. So these are these tasks up here that are being, that it's actually doing it. You can see that these robots, they generally speed them up about 1.5 or 2 times to make it more fun for humans to watch. But you can see they're not particularly fast in the world, but they do operate.
Okay. So I'm looking at what's going on in Berkeley there.
Yeah.
They're using the UR5 for that. And it looks like they're doing some kind of almost like polishing or buffing over a sculpted surface. And
Yes.
there are some pretty simple heuristic algorithms to be did, because you're using the force feedback to kind of follow. You're not even teaching it any points.
Right. Right.
So it's using a little bit of trickery to be able to kind of pull that off, which
Right.
may be the reason why the training, because that is like super specialist.
Yes.
It's a really nice way to be able to take a complex curve that normally would say, oh, if I want to buff a surface that's like this, and I have the robot do that, I train all the points along what could be a complex spline surface.
Right.
Now, what you can actually do is you can train a start point and an end point and tell the robot to go in a straight line.
Right.
So you just give it a start and end. But what it does, it has force feedback or compliance on that buffing wheel that it can sense, and it knows, oh, to change the orientation, the amount of pressure, and whether it needs to lift up and down. So basically it like automatically follows that thing. So it's kind of cheating in a way, because you're teaching this complex surface with 2 points.
Right.
And so it works really well heuristically. And I could see that maybe that's one of those things that's not so easy to then train in GPT or in RTX. Yeah.
Right. The one above it, the rail at UC Berkeley, that one is really cool, because that's actually placing a flexible cable into that slot. And that is by no means an easy task when you start dealing with flexible objects.
No way. Yeah. So it's trying to figure that thing out. And that there again, it's you've got a vision system that's trying to figure out how that's going to work.
Right.
So
But I mean, that's good. Look at that. And maybe it looks like there's a yellow and a red tab on it, and maybe it said place it in between the yellow and the red tab, so it knows that those are it can't just keep pulling it forever. So
yeah. And I'm wondering if that's also just to give a couple of reference locations.
it could be. That could also be the case.
Spline is that they're looking at. Yeah.
Right. So anyway, that's a very impressive move. The University of Freiburg down at the bottom with the drawer opening, again, is, I guess, a more or less simple task, relatively speaking, although, it is a significant 3D object. And you've also got the NYU one, where it's opening up a more complicated door, because it pivots, since it's got a hinge on it.
Right. That one's a pivot. So that one is, they're just kind of going along, and the arm, it does want to pull it straight out. So it kind of knows it straight out, but you're right. The NYU one is a little bit tricky, because you've got that hinge, and the arm has to track the hinge as it goes around.
Exactly.
And the other thing you have to understand is, like, even when we do it with our hands, as you can only open it so far. If you open it too far, your hand gets caught, and the door starts to bang into your wrist. And you can almost see that if it goes past 90 degrees, you're going to get a self collision there that you don't want to have.
Right. Yeah. And also, if you try
it's like, don't go much further. You're going to get in trouble.
And also, if you tried to force it past there, you'd break the hinge too, because it would eventually
It's a question
overextend.
whether, yeah, some hinges are designed to only go like 90 or 180 or 120 degrees.
Right.
And it's the rare one that seems to allow you to open up 180.
Yeah. Yeah.
So yeah,
Also, I think on the end of that robot arm is an iPhone or a phone. It looks like if
maybe.
you once it starts moving forward, yeah, right
Oh
here.
yeah, yeah. Oh, okay. There's a phone there recording what it's doing probably.
Yeah, so it probably is just recording, although it might actually be used as
Could
part
be,
of the sensors.
could be that like they want to show that using a low cost phone works.
Yeah,
Because
exactly.
a lot of vision systems that you put on the end of robot arms can cost as much as the robot itself. So
Right,
it's
right.
like, well, wait a
So,
minute,
so these are
let's
actually
get
really
something cheap.
interesting. They're really interesting use cases because these are a wide variety of robots here and
Mhm.
wide variety of systems and a lot of labs and things. So you've got these systems that are running on fairly low cost hardware, reasonably,
Mhm.
within reason and everything. And then let's see, we get the emergent skills. Yeah, this one down here is really cool. So these apparently are tasks that it was not trained on. They had never said move apple between can and orange. So that's a new task. Move apple near cloth, move apple on top of pot. The one on top of pot, I wonder about because I feel like it should have flipped the pot over first, because in my mind, that's placing in the pot.
Yeah.
Like I would flip the pot over and stick it on top, but I don't know. Apparently that's what it was supposed to do.
Yeah, but
Uh,
on
yeah,
top of pot, or wouldn't you say on bottom of pot? Yeah.
yeah. So I don't know. I don't know. That's a linguistic semantic thing because the language is a little bit iffy. So anyway, but you can see these tasks. So these are tasks that if we scroll back up to this data set, all of these data sets, there is no task involved in those data sets that are move object between these other objects, specifically like that, or move this thing near the cloth specifically, or on top of pot. So it's demonstrating the ability to demonstrate demonstrating emergent behavior. There we go. So this is emergent behavior. This is not pre-trained behavior, and that is a really big step change. It's one thing for Boston Dynamics robots to do backflips and stuff when they program it in and they are very carefully specify how it's going to do it. It's quite another if you said, okay, you can do a backflip. How about doing a front flip now? And Boston Dynamics robot did that. Now, maybe it'll be able to do that someday, and that'll be super cool. But that's a different skill. It's related to the other skill, but it's different. And so it requires the brain of the thing to figure out what it is, how that relates to skills it already knows, and then how it's going to execute that. So this is very cool. And as it says down here, demonstrates skills it was not capable of previously, including better spatial understanding. For example, if we ask the robot to move apple near cloth instead of move apple on cloth, which was one of the trained tasks, the trajectories are quite different. By changing the preposition from near to on, we can modulate the actions the robot takes. So these are similar actions to what it's been trained on, just never exactly the same as that before.
Right.
But
It's
yeah,
it's interesting. Yeah, I was going to say it's like, well, wait a minute. It understands prepositions and like right down there. There it is in the text. Yes, absolutely. So
right,
near, on, above, next
right,
to, by. So that's interesting. You can see how the language model in there is interpreting that, and then from
right.
it is able to figure out the output that actually satisfies that. That is impressive.
Yeah, and I believe it's using Google's Poly. I think that's I
Hmm.
think PALI, if I'm remembering right. Anyway, I believe it's using that as the basis for the natural language interface. And then it's translating that to the vision token system. So there's a lot of natural language. This is really interesting because I remember so this was less than a year ago, right? It was November sometime when OpenAI released ChatGPT 3.5 or 3. And everybody said, well, this is
Yeah.
great, but it's never going to have any practical effect in the world because it can't interact with people in a physical space. And here, less than a year later, we've got in fact, it was only a few months
Mhm.
later because Google put out RT1 back in like June, I think, something like that, March, April or June. Anyway, so it wasn't that long before they were like, nope, this actually works in the physical world. It's fine. So this is very impressive progress that's going on here. Um, and then we've got, I think this is the bottom. Yeah, responsibly. Okay. So, yep, they're doing it all responsibly. They got the ethics and all that good stuff. So Good for them. The R-2-X shows that combining data from other robots into the training improves the range of tasks that can be performed even by a robot that already has a large amounts of data available, but only when utilizing a sufficiently high capacity architecture. So I believe they said they released the R-1-X architecture publicly, but I don't think they're releasing the R-2-X. So they're keeping a little bit of something to themselves. So, but anyway, yeah, so R2X is 55 billion parameters. So that's pretty big. I mean, that's almost the size of Llama's biggest large language model that they have. It's so it's a large model.
Right. And the training sets are what's important.
Yes.
And that you need to have a sufficiently large training set. So, having 1 million is a good start.
Yes.
That's sort of almost the bare bones minimum that you would need to start to see things like this. And as
Right.
you get more and more of it, and we might be able to get into that virtuous loop now that
Right.
we can now have the robots start doing all kinds of different training tasks now
Right.
that we've kind of got that bootstrap going, and then just start recording more and more of those things, and you get more and more training data. So it'll probably start to really increase exponentially now.
Yeah.
Especially when you're going to see everyone's going to be interested in this.
Right.
And is going to want to try it themselves. So maybe the days of the household robot are a little bit closer than I've been thinking.
That could be true. That actually could be true.
It's I've had a feeling it's still a few years away, partly because of sort of understanding what's going on in there, and the other is the dexterity. So none of those robots you see there are really going to be sufficient for being able to go into your house.
Yeah,
because
as you said at the
all
beginning,
bolted, or they move around. Some of them don't move at all. So most of them are standard robots that are tabletop robots, and that's it. And the Google robot, I think, has mobility, and maybe a couple others are out there. So, and even though it's not a humanoid robot, I think it will apply to the humanoid robots. You'd be able to use that for training sets.
Right. It is a very limited scope data set from what I understand, because it sounds like it's only for the arm. It only uses 7 degrees of freedom. So, I mean, the last degree of closed and open is very rudimentary.
That's just open and close. It's not like how to grip it. Yeah, I agree. You're going to need something a bit more, but it's a place to get started.
Yes.
Definitely a place to get started.
Right. And again, if you look back at the ImageNet, I'm trying to remember, was it 256 by, I think it was huge. It was really huge. It was 256 by 256 square images, or maybe it was only 128 by 128. But anyway, it seems tiny nowadays, these little itty bitty postage stamp size images, but compared to 32 by 32, which was kind of the standard before that, it was a massively bigger image that it had to deal with. And it's a really big challenge. So, you might go like, oh, this is only an arm. It's only 7 degrees, or it's only 7 things that's recording for each moment of time. But it's a starting place. Like you said, this is not where it's going to be in 2030. This is where it starts now, but it's a huge advancement. If you look at what happened from 2012 over the next 11 years, it just went completely crazy. In fact, really, the ImageNet aspect of things was a solved problem probably by 2016-ish, somewhere around there. I mean, it was getting better than human rating by 2016, 2017. So it only took about 5 years to go from the introduction of that to it completing the tasks of identifying better than humans do. So that it's incredible how fast this stuff goes when it happens. Now, a robot's different than images, so it will take longer, but also people can throw this in the virtual world and have it do millions, hundreds of millions of iterations of this stuff in a virtual environment as well as simulation.
Right.
Speaking of visual components,
you're going to have to.
We'll give you a little shout out here because, speaking of simulation.
Yeah. And you're probably going to have to. What I'm imagining is, again, this is something that Jeff Lutz had pointed out, that when you start to get the bots doing, let's say, a similar task on the factory floor, are they going to just keep on doing exactly the same, or the bot's going to somehow figure out in some way an easier or better way to do it? Not necessarily sure, because as we discussed, you almost need like millions of iterations before you get that kind of breakthrough, like the 2-minute papers with the seekers and the finders of like, what's the little trick we can do to get around there? And as we talked about with, having the 2 optimists playing the keep away game,
right?
Man, that's going to be like a lot of optima you're going to have there, and a lot of time for them to be able to kind of figure out the magic trick is like to wear that guy's batteries out while you're doing it easier, like some
Right.
other little stuff. So I could imagine that to get it to be better on the factory floor, you would be taking a lot of what the bots are actually doing. Say, okay,
Right.
this bot is doing this particular exercise, put it in there. And now that let's do like Monte Carlo it, or
Yeah.
do some sort of genetic algorithm on what it's just performed and see what else we can kind of come up with in the background.
Right.
So I think there's going to be a fusion between the two, that there would be a lot of simulation based on what we're seeing, because the operations of the factory floor will give you really good data because it's real physics we're talking about now. Whereas the
Right.
simulation, it's an approximation of physics, doesn't quite have everything in there. So if you can start to get more data, and if the data of how objects are interacting, at least in that particular cell, can also go into another neural net that, almost like stable diffusion, that
Right.
rather than generating images, it's generating physical effects that are like really darn close to the real physical effects. So you're not modeling things like, friction and compliance and all these other things. It's just there
Right.
for you in a way. And that means you start training on that. And then from that, that's probably where you find, oh, this is the best way to do this particular operation. And then you can start to deploy it back on it. So I could see that there could be, this really quick connection between what's going on there and, maybe Dojo in the background that's kind of crunching and doing it. And again, going back to like our Dr. Strange analogy there, that he sits there and like he imagines 49 million different scenarios, just
Right.
playing them all through in his head. In a sense, we do something like that too, but it's kind of funny about training is that if you work out really hard, or you're trying to practice something and you're just not getting it quite right, or you're doing some homework problems, they always say sleep on it. And it turns out that when you're asleep, whatever's kind of going on in your brain, everything gets readjusted. The next day, suddenly, wow, that tennis swing I was working on that I was really bad at yesterday, today I'm really good.
Right.
That math
Right.
problem I didn't understand. Oh, I get it right now. So it'll be sort of the same thing, that I think you want kind of that background process every now and then, examining what the bot is doing and deciding,
Right.
almost a shadow mode, which is what FSD already does already,
Yeah.
right? Something
Yeah.
like that. So
Yeah.
yeah.
Yeah. I think all of this stuff kind of ties together, and this clearly relates to what Tesla's doing. Although I have a feeling that their version of the vision, or the physical tokenizing, is probably more sophisticated than 7. It's probably joint
It
rotation.
is because
Yeah. And
yeah,
lots
because you
of
got to have
bits.
everything with the fingers, because there's different kind of objects that you're picking up. It's not just open and
Right.
close. So those
Right.
grippers have some sort of compliance that they kind of close,
Right.
and
So
when they
they
get
just,
down, they'll automatically do it. But yeah, it's really going to come down to what's the grip state and other subtle pieces of information. So I was
right.
thinking about this the other day, is that everyone keeps on wondering, it's like, oh, we're going to need to put more sensors in the fingers and all these other things. And we all know it's like when you get in a car, you talk about how you can feel the road.
Yeah. Yeah. Yeah.
I mean, you can, when you're driving it through that steering wheel, you're feeling everything. You can tell whether
Right.
it's a gravel road you're on, whether it's a smooth road, whether it feels a little bit slippery, after it rains. There's just all these other things that you are sensing in your body
Right.
and through it. And it's like, but you don't have any sensors on the tires. But how
Right.
is it that somehow you can almost feel things through the tires?
Well, what's that famous line of flying by the seat of your pants? It's like, if you don't have instrumentation, I'm not a pilot, but the same thing with
Yeah.
driving, you feel it. You're kind of like sitting in the thing.
You feel it
Yeah.
in your torso, you feel it in your hands.
Right.
Sometimes you feel it in the gas pedal, you feel it in the brakes. I mean, all that is there. And I will be saying, yeah, but that's because you've got sensors back in your fingertips or something like that, that you're able to kind of pick that vibration up. Well, what I think is going to happen with Optimus and others is that the sensors don't necessarily have to be at the fingertips. So
Right.
we've already talked about the force feedback that you're getting, the back EMF that's getting an idea of the clenching force. But
Right.
there could be other things, other vibrations and things that could be picked up by things that are actually in the controller. So you could be
Right.
putting your sensors actually not at the tips, but back right where the motors are. And they would probably
Right.
be absolutely non-intrusive. They're just in there, and they just become part of this additional data stream that you
Right.
feed back to give you, what does this feel like right now, to get
Right.
that same sort of remote sense that we're always able to do.
So, I mean, you could think about, like, just take a steering wheel vibrating, that you're like, well,
Mhm.
Optimus couldn't detect that. But if you thought like a steering wheel going like this, there's going to be a lot of back EMF through
Mhm.
all of the actuators.
It's
And
going to
so
be
it's going to
feeling
go,
that.
it's going to go from a line like this to like you'll get some, and so it will definitely be able to sense that there's.
Who says Optimus wouldn't be able to sense that
Yeah.
vibration? You know, that vibration
Right.
could be something you put in there with some sort of acoustic sensors that are built in or something else. I
Right.
mean, first you'll be able to hear a little bit, but I think you'd be able to put something in there because it's just
Right.
kind of a form of sound. And
But
if
I
you
don't,
think about
what
it,
I'm
if you
saying is
come
I
up
don't
with,
even think you need to add sensors. I think it could do it with what it has right now because it has detectors.
you could do a lot.
Yeah.
Yeah, you could do a lot, but you don't need the sensors out there. You
No,
could have
no.
it because the motors themselves have encoders in there, which are the sensors
Right.
and part of the back EMF. And maybe you add just a little bit more in there to detect other vibrations that are coming down the line. And maybe
Right.
that's like like a piezoelectric crystal that you could put in there that would be able to sense the vibration. And then the other part of it is that it works both ways, right? You could use that to actually send a signal. You
Yes.
could vibrate that string that you have, and that's now going to go out, and it's going to, and depending upon what you're touching, what comes back is going to give you a different signal.
Right.
So I have a feeling that there's these other ways of both a passive and active sort of sensing that won't actually require anything on the tips,
Right.
because you have the wires there. Basically, the wire is your sensor. Think
Exactly.
about it. It's attached to it. Just like put the sensory part back here and don't put it on out there.
Right. Right.
And eventually you would probably be able to gather enough data to get an idea of having a hand that works tactically pretty well without overcomplicating the sensor suite.
Yeah, these are all like, I don't know. I was thinking about this because I have this dropper, and this sort of motion is kind of a delicate motion of squeezing the dropper head. And I probably, though, Optimus could probably do that right now because part of it's also visual.
It is visual. I do that all the time. I'm taking it up there and I'm looking at it. It has nothing to do with my feel up here. I know I've got to squeeze it a little bit, and then I see that drop go, and now I'm done.
Yeah.
So that's what we've been saying all along. It's the visual is the key. It gets connected in. That's why we know how to hold this bottle, because when we see the bottle, we know the expectation of what the hand grip is going to have to be. If I'm going to pick up a dumbbell, I'm going to like automatically know, oh, I'm going to have to clench really hard.
Right.
So that's the visual input that sort of tells you the expectation of what you have to do.
I just realized that we'll probably have Optimus jokes, because you have a thing where you make something that looks just like a dumbbell and it goes to pick it up and it goes woo, like just like with a human being, like flailing, filling back. So so you're gonna have your poor Optimus in your house. You're just gonna be playing jokes on it all the time, like setting up things that look like other things.
You go to a joke shop and you'll pick up something that looks like a cinder block. It's really light. Like, oh, like I throw it over, and he's expecting it, and like he catches it and expecting to fall back, and he falls forward because like, wait a minute, I was expecting something different.
So there we go. And then of course, when the robot overlords take over, they will remember. They'll be like, I remember that.
Yeah, I remember these jokes. Yep.
Yeah, I got you here. Very, very cool. So anyway, yeah, this is, again, fantastic, amazing news by Google DeepMind and also Berkeley, NYU, all these, University of Freiburg, all these other ones that were participating in this. This is a marvelous moment for kind of open source, sharing a lot of data, creating a data set that is similar to what ImageNet was 11 years ago, well, 15 years ago now. And it's a real beginning. And this is one of those things where, yeah, they are competitive with Optimus, but not really. I mean, their robots aren't, even Google's robot, it wheels around and it has one arm with a gripper. So, this is not apples to apples comparison, but it's definitely something that, the Tesla AI team is always keeping up with the latest papers and stuff. So they will, of course, have already read this paper, and they will have looked at it and said, either there's like, all right, we're already doing all of these things, or more than likely thwill say like, oh, that's a cool idea. Oh, that's a cool idea. So they will, probably roll that into future versions of what Optimus is doing.
As will all the other humanoid bot manufacturers. So I see, this is just bullish on the whole idea of a humanoid bot.
Yeah.
Not just for Optimus, but in general. And I think that's a good sign, because if Tesla was the only one doing this, everyone would just say that's pure insanity.
Yeah.
But the fact that everyone else is doing it means there's a certain amount of credibility and expectations that this is really going to work. And there's a race going on. People want to do it.
Right.
So, I mean, we see Cruise and Waymo out there spending billions of dollars because they believe that autonomous driving is possible.
Right.
So again, that's kind of bullish for FSD. So it's not necessarily competition, but it's a good sign that, Elon's not off on some really weird thing that is pure science fiction and will never come to fruition.
Yeah, the weirdest thing he's doing right now, according to competition, is flying into space because nobody else is doing it at all. But you know, in
Yeah.
terms of these things, everybody else is doing it. A lot of other companies are doing it.
Yes, yes. And a lot of other people are also going after space as well. And a
Yeah,
lot of it's these smaller companies.
right, right.
It's the big ones that have been really failing at doing anything. And you see
Right.
a lot of these startups that, have already gone out and also achieved orbit and
Yeah.
just new construction techniques. So I think in the next couple of years, SpaceX is going to see some competition, but it's not going to be coming from who we think it's coming from.
Right.
It's going to be some of these startups that
Uh,
will have some pretty novel ideas.
Yeah, that was somewhat of a joke. I was being facetious, but I just like with cars, especially right now, you know, you being up in Michigan with this UAW strike, the legacy automakers are becoming irrelevant very rapidly. And the competition is coming from startups, you know, from things like Rivian, from
Yeah.
BYD, from a lot of Chinese companies. There's a lot of startups that are growing very, very rapidly. So yeah, it seems to make
Oh,
sense.
and speaking of being up here, I actually saw a lyric in a
Did
neighbor's
you?
driveway,
Ah,
and it
yeah,
wasn't like a loaner. It's like I looked at the license plate; it wasn't manufacturer plates or anything, and it had a border around it, which was clearly the alma mater that they went to. So
right,
it's like, okay, that's not something you're going to get from GM. So they actually bought it,
right.
but it's white. I'm not sure that the lyric does. I mean, the Celestiq looks horrible in white, and the lyric, not much better. I would have picked a
Yeah,
different color,
yeah.
but it seems
Oh,
like all the ones that we're seeing that GM, the first runs that GM is doing, looks like everything's white,
huh,
even though they showed, originally what the Celestiq and everything was like. The Hummer, I think I've only seen white
right,
on
right.
the roads. I've only seen a white lyric. You know, people have got pictures of the Celestiq. It's only white. It's like, well, what's going on here? I guess
Right.
they haven't tuned in the paint shop yet or something like that.
Yeah. Yeah. Maybe they just have they only have the one paint shop that only does the white. That's it. You have any color you want as
Yeah.
long as it's white.
So right now the production volume is just so low. This is what we're going to do. And then
Right.
eventually, if things start to take off or people really like it, then we start giving them the selection of colors. But it's
Right.
it's hard. I mean, you think it's just you just put a different color in there. It's like,
No. No.
it's
No.
it changes the viscosity and everything of the paint gun and all the stuff that's going on, and then you just don't get quite the same effect. So yeah, they tune it in for white. We'll say that'll be fine for now, and you don't like the color, wrap it.
Yeah. Speaking of that, did you see that the video of Autoline video where he talks about the fact that they changed the charging port on the side is just black plastic and I was like, holy crap, that's right. And that's so genius because that's just something you don't have to associate with a particular car. Because of course you have to paint every part that's painted has to stay with that car. And this then just becomes a part you just slap on because it doesn't match any of the paint, which is brilliant. So
Right now, if you look at all the other EVs out there, the Rivian, the Ford Lightning, everything else, they have that port like a big gas port that
exactly.
you've got to open up that big lid, and you've got to make sure that matches. And for some reason, I think I saw in the Ford they have it like on both sides, but there's only
Yeah.
the charging port in one. I didn't quite understand that. It's like, well, we're just kind of putting it there so it kind of matches the other side. Like
That's
parts you don't need.
yeah. Also, if it's non-functional, it's just going to be confusing because people try to open up the
Yes,
one that
yeah.
doesn't work. So
Yeah. So I'm not sure what that was about. So again, yeah, that's added complexity because of the location where they put it. We just cannot make it plastic because it would look stupid. It has to be the color of it, and
right.
that has to go through the paint shop. It has to have the exact same batch of paint. Otherwise, even though like midnight silver, it's like, well, it'll be a slightly different midnight silver than the other one that came out 3 weeks ago. So
Yeah. Yeah. And that's the reason I found that out when our car got dinged, which was the major cost of that repair wasn't pushing the aluminum back out and reshaping it properly. It was repainting it to match everything else. That's a multi-day process for the body shop to work on. It costs a fortune to do. So yeah, it's every time you can reduce the paint is a good thing pretty much. So anyway, so we've gotten off topic of robots a little bit, but anyway, so all to the good. Obviously, I think what you said is right. When we're looking at this, the more people who are interested in doing this, the better the signs are for the public interest. And there's going to be, as you know, I mean, that's the industry that you work in. There is plenty of room for a lot of companies to be working in this, especially when we start working towards humanoid robots, where the limitations are not giant factories, but really anywhere. anywhere a human can go, these things can go.
Mhm.
Yeah.
Yes, and there's probably way more applications for the humanoid robot than I'm aware of right now.
Right.
I'm
Right.
thinking narrowly in the factory, but there are definitely a lot of other places probably outside the factory. They may be very close to be able to do that. And that's sort of what's going to limit how many bots are built. It's
Right.
not that they're going to be complex to build. There's a certain couple of bottlenecks on Optimus, but I think they could be smoothed over. So
Right.
I know Randy Kirk thinks they're going to do 1 million next year. And like, that's a lot, and
That's bullish.
Tesla does not need 1 million. They don't need 1 million because they don't have 1 million employees that they need to replace.
Right.
And the whole idea is that one Optimus might be able to replace 3 employees if it runs at the same rate.
Yeah.
Because of the 3 shifts. So it could
but
be
even on a
much smaller
conservative
number.
basis, you're not going to replace all 120,000 people.
No, you're not. You're not. So I'm seeing that, next year they might be able to find some use out of 10,000 bots.
Right.
They might be able to produce that. Some of the uses might be not actually using it in the factory doing anything useful, but maybe it's training. Maybe again, it's that room full of bots are just going around and just, training, doing that. So that might be part of the reason. I just can't see them being able to absorb 10,000 bots next year, unless they have a lot of people that are ready to buy it, which means it has to be ready to be bought.
Right.
And I don't think it's quite there. You're ready for other people to use it. And then as far as the production bottleneck, the assembly just looks easy. I mean, you just get all those components and they just come together. The question is, how easy is it to generate the components? And the main component, I think, is that, 40 actuators we're talking about. For one bot, you need 40 actuators. And what's that line going to look like? And can they scale it up and start pumping them out? Is it all ready to go?
Right. And let's not forget about the hardware 4 board. Now it looks like it's a half a hardware 4 board because it doesn't have the redundancy. But if they're going to be trying to produce, let's say 2.4 million vehicles next year, they need 4.8 million hardware 4 chips already just for their cars. So, I mean, if it's 10,000, that's a rounding error and no big deal. But if they're looking at building a million of these things, then that's a significant.
So 5 million you're going to need.
Yeah.
And so you would have to tell them ahead of time that you need that. I don't think you just say, oh, add another 20%.
Yeah, yeah, exactly. And these companies are probably working near capacity already anyway. So it's not like they can just turn up the volume more. So yeah.
Right. Yeah, exactly. NVIDIA and everyone is pumping out those chips as fast as they can.
Right.
And Tesla has already gone in and said, yeah, we'll go ahead and take that. But they're going to have to know what the plan is and tell them, okay, expect 4.2 next year. And then we're, the year after that, what are they going to be at 3 million, something like that? So they're going to need 6 million just for the cars.
Right.
And then say, oh yeah, now give us 7 million total. We'll see.
Right. Yeah. So I think you're right. I think that the construction of Optimus will be relatively straightforward, the final construction, but it's building the actuators and again, batteries, again, small batteries, but 1 million is a lot. But yeah,
1 million. But
and then
I think what is it? 1 million? Is it like 300,000? No, is it around 30,000 Model Ys? I think in batteries.
Yes.
So it's like about somewhere around 35 Optimi will consume the batteries of one Model Y. So if you take 1 million and divide it by that, what do you get? I think it's somewhere around 30,000, something like that.
Yeah. So it's not that much.
Yeah, it's basically it's the number that you miss on your Wall Street quarterly deliveries, right? That's what we're talking about.
Speaking of which, the new Model Y rear-wheel drive just came out in the US and it looks like it's using LFP, and they've removed the standard range structural battery pack one from the lineup, which in my mind means that they have reserved all of those for Cybertruck. They have probably they've removed the Model Y from the using 4680s pipeline, which indicates to me, number one, again, they're still having problems ramping it as fast as they want to, because if they had so many, they wouldn't care about doing that. But also it's cheap, man. That new Model Y is cheap, but that it seems like they're just reserving everything they've got for the Cybertruck to try to ramp that thing as quickly as possible. So at least that's my guess. So yeah, so interesting stuff. All right, I have kept you for an hour. Thank you again so much for talking. I know it's a busy day for you, so I appreciate the time. And Again, everybody, thanks Scott. Make sure you follow him on X, not Twitter. I was going to say Twitter. My goodness, slap myself. And of course, do the liking and subscribing and all of that good stuff. And Scott, thank you so much for talking through this. This was fantastic and really interesting news, very bullish news. And thank you again for being with us. And of course, we will see you in the next video. Bye-bye.
Bye-bye.